All right, we'll do some examples of Kepler's third law here. So let me do this. All right, all right, and I'll do some examples of the other. Well, I'll do them towards the end. Okay, so I want to just get through the PowerPoint slides, and I'll do some examples. So again, the period squared in period must be in years, and the semi-major axis cubed, where the semi-major axis is in what are called astronomical units. I didn't say that in the last video. So one astronomical unit, for example, is the distance between the Earth and the Sun. So Venus is at about 0.7. Mercury is at about 0.4 astronomical units from the sun. So remember, this is the average distance. Mars is about 1.5, roughly. All right. So when if a planet is orbiting the sun, it has to follow this third law. All right, that's extremely important. And this is the original Kepler's third law. Later on in the next chapter, we're going to modify it. Isaac Newton, as a matter of fact, modifies it so that this can be used anywhere in the universe, not just something orbiting our sun. All right, so that's that is the third law, as I mentioned. Kepler even just to go a little bit further, he realizes that for the planet to go in this orbit, to obey this equation, p squared equals a cubed, there must be some kind of force that is holding the planet, from wandering off into space. And so he actually, proposed at the time, was at the time it was very reasonable. Nowadays we know it's not right. He actually proposed magnetism because during his time, 400 years ago, magnetism was being studied, and so he proposed that there was this force of magnetism that was causing it. We know, of course, now that it's gravity, but it took Isaac Newton to come along to state that. All right, so there's one person between Kepler and Newton. So anyhow, as I said, this is the third law can be used. So one of the things that we do in astronomy, for example, is you can measure the period like that. That's something that you can observe what the period of a planet is, and then from that you can work out mathematically what the semi-major axis is. And if you know what the actual distance between the Earth and the Sun is, which is, of course, one astronomical unit, you could work out, if you know, for example, we know very, very well that one astronomical unit is 150 million kilometers, all right? So that's, that number has been well established, of course, in modern times, we know that. And since we know that, we know the distance to Mars, we know the distance to any of the planets, to Jupiter, to the asteroids, things like that. Anything that's orbiting the sun is obeying this equation, and we can convert between astronomical units and kilometers, or astronomical units and meters. All right. So this is the individual, of course, the very famous individual, Galileo, the Italian Renaissance astronomer. You can see there's his dates. By the way, when he passes away, which is in 1642, that turns out to be some cosmic coincidence, if you ask me. That this 1642 is the year that Isaac Newton is born. All right, so Kepler and Galileo lived at the same time on the planet. Kepler lived in Germany, although he wandered around a little bit because there was a big war going on in Germany at the time. I think it was, if I'm not mistaken, it was called the 30 Years' War. Not that that's important to us these days, but there was this war taking place, and but Galileo and Kepler corresponded with each other. They never, as far as we know, never actually met, and didn't really influence each other's ideas. Like, for example, the stuff that Kepler had done should have influenced Galileo, like especially the third law of planetary motion. But Galileo was, yeah, Galileo was an individual that was extremely bright, extremely smart, and he really didn't like um, rely on other people, to say the least. All right. So one of the things that probably the most famous thing that Galileo does as far as astronomy is he takes a telescope that he built himself. Now we know that he's not the first one to build a telescope. There was some person named Leeuwenhoek. We think that that's the actual first person who built a telescope. But once the telescope was invented, it became became widely known, and Galileo, just kind of hearing about it, says, "Hey, I think I can grind the mirror. Sorry, not mirrors. The lenses. They didn't use mirrors until the time of Newton, but he grinds the lenses himself, and he invents his own telescope. And he, as far as we know, and it's actually a well documented year. The year was 1609. All right, so 1609, Galileo turns his telescope to the night sky and makes incredible observations, and of course writes a book about it that is extremely influential. In the book, one of the first things he looks at is the moon. He notices the surface of the moon, and he compares he notices there's valleys, there's mountains, and he even poetically, if you will, compares the valleys and the mountains to the Italian countryside. And of course, we now know it's very, very different than the Italian countryside. Another thing that Galileo does is and of course, this contributes, we think, to his blindness later on in life. He turned his telescope not when the telescope was directly overhead, or not when the sun was close to noon or something like that. But he turns his telescope to the sun, and he notices that there are sunspots. So he did this early in the morning and right before sunset. And I would imagine he knew not to, at least not to look at the sun when it was really high in the sky, because it would have instantly blinded him. But this really did cause a lot of retinal damage, and it's well known that the last 10 years of his life he was completely blind. But he, again, he noticed sunspots, which no one had ever noticed. And you can see them nowadays with, you got to use a filter on your telescope, and you got to make sure you use the right filters on those. At any rate, Jupiter, and he turns to the planet Jupiter, and he notices these four dots. And this is an actual drawing of Galileo, sometimes you can see three of the dots. Sometimes three dots are on one side. Sometimes you can only see two of them, and they're changing position. But there's these four of them, and he named them. So this is how they're named. The one that's closest to Jupiter is Io, Io, Europa. Ganymede is this next one, and then the farthest one out is called Callisto. So these are actually the four brightest moons of Jupiter, the four largest moons of Jupiter: Io, Europa, Ganymede, and Callisto. All right. And when you see them, like three of them on one side, that's they're just orbiting the planet Jupiter. And he realized that these objects were orbiting Jupiter, which goes right against what Aristotle had told everyone, is that all motion in the heavens, um, including these little moons, should be going around the Earth. But they're clearly, through the telescope, you can see they're going around Jupiter, not around the Earth. All right, so that was a big deal. He also turned his telescope to the Milky Way, and he found that there were incredible numbers of stars. And he had, we have his very, very primitive telescope preserved, and it was not it was not a very powerful telescope, but he made all these incredible observations. One of the things that he did is he noticed that when he looked at Jupiter is one of the brightest things. I'm sorry, Venus. He looked at Venus, which is one of the brightest objects in the night sky, besides, of course, the moon. Venus, through his telescope, he could see that it was going through phases. Right, there was a gibbous phase, there was a crescent phase, and so forth. And so he recorded that, and of course he believed Galileo, had read Kepler's book and realized that, or accepted that the heliocentric model, the model which puts the sun at the center of the solar system and the Earth as a planet going around the sun, was correct. And for the motion of Venus around, the fact that you can observe phases, really, there's no explanation for that in the geocentric model. You would never see phases in the geocentric model. Only, if the Earth goes, if the Earth and Venus go around the sun and not around the Earth. All right, so Galileo, he's also the inventor, or one of the inventors of modern science, or using what's called the scientific method. He investigated actual physics problems. He works out the laws, some of the basics of the laws of motion that Isaac Newton will further mathematically. Although Galileo was a pretty bright mathematician himself, he did understand basic algebra and so forth. Let's see. Now, before we get to Newton, it says here at the very last little thing, it says he was because of this. Again, it's really hard for us to understand this nowadays, but the Roman Catholic Church really controlled a huge portion of the planet at the time of Galileo, roughly 400 years ago, and they had said that the heliocentric model was, basically against God, and if you believed in it, you were a heretic. And so, since Galileo wrote a book about the heliocentric model and said, "Hey, look at all this evidence that I have," it really upset Rome, right? The Pope in Rome, and Galileo was brought before some prosecutors of the Roman Catholic Church. Of being Italian, he was Catholic as well, Roman Catholic, I should say, and he was brought he was brought before the Inquisition, and it was very, very difficult because he was a really smart guy, and they kind of humiliated him, and he finally he said, no, everything that I said was wrong, and that the sun goes around the Earth, and